In this lecture, we are going to take a look at degenerate perturbation theory. But before we go into that, let me briefly recapitulate what we had learned about perturbation theory in the first lecture in this series. So, remember, we have these basic ingredients. We have H0, which is an exactly solved Hamiltonian in the sense that its spectrum, its eigenvalues and eigenvectors are perfectly known. So, the eigenkets are phi n and eigenvalues are epsilon n. It's assumed that we know all the eigenvalues and the corresponding eigenkets. We also assume that these eigenkets are orthonormalized, that is, the inner product with each other is 0 or 1 if you are taking it with itself, and they form a complete set, which means that this particular sum of outer products, which are basically projection operators to individual eigenspaces, they add up to the identity, which essentially means that any vector in your space can be written down as a linear combination of these eigenkets. So, that is all about H0. In addition, we have another ingredient which is V. This is a perturbation which is in some sense small compared to H0, and if that is so, if V is in some sense small compared to H0, we can use perturbation theory to determine the spectrum, at least approximately the spectrum of H, which is H0 plus V, which means what we are really seeking are the eigenkets psi n and eigenvalues En of H, which is H0 plus V. Now, in order to facilitate the process, essentially to keep track of how many powers of V we are using in an expression, we introduce a formal parameter lambda. So, we start by letting H be H0 plus lambda V. At the end of the calculation, we will put lambda equal to 1, which will bring us back to H0 plus V. And when we do that, in addition, we are going to assume that the energy eigenvalues En of the full Hamiltonian, as well as the energy eigenkets psi n, can be expanded in power series of this parameter lambda. So, En is En0, which is the 0th order term, plus lambda En1. En1 is the first order correction, and so on. Similarly, psi n, the eigenket, can be written down as psi n0 plus lambda psi n1, and so on. And psi n1, psi n2, etc. are the first order, second order corrections to the eigenket psi n0. Now, when we plug all of these things back into the Schrodinger equation, namely here, and then compare individual powers of lambda, we end up with the perturbation theoretical equations of various powers, and these are things we met in the first video. So, we get, for lambda to the 0, we get H0 to psi n0. This is basically comparing both sides of H psi n equal to En psi n and picking out only terms which are independent of lambda. So, we get H0 psi n0, H0 the Hamiltonian acting on psi n0 is En0 psi n0, lambda 1 from picking up powers terms which have lambda to the power 1 on both sides, we get H0 psi n1 plus V psi n0 is equal to En0 psi n1 plus En1 psi n0, and so on, and we can write down the general term which we get by comparing coefficients of lambda to the m on both sides. So, this is all we had already done, and we had also gone further and talked about the first order equation, 0th order equation first. The 0th order equation, of course, is this. This is obviously the eigenvalue equation, or actually the eigenvalue equation for H0, which immediately tells us that En0, the eigenvalues, are nothing but the eigenvalues of H0, and we already know all the eigenvalues and eigenvectors of H0. So, what we do is identify En0 with the eigenvalue epsilon n and proceed from there. Now, if epsilon n happens to be a non-degenerate eigenvalue of H0, then this identification immediately tells you what psi n0 is. Then psi n0 has to be nothing but the eigenket phi n. There is only one eigenket phi n corresponding to epsilon n for the operator H0, and then psi n0 has to be that. Of course, when I say has to be that, you have to remember that you can have an overall multiplying factor, or if you are insisting on both psi n 0 and phi n to be being normalized, then you can still have an overall multiplying factor which is a pure phase. But we ignore such distinctions. After all, kets which differ by just a constant phase factor are essentially the same kets as far as physics is concerned. So, if epsilon n is a non-degenerate eigenvalue of H 0, then psi n 0 can be immediately identified as the ket phi n. So, this is the basis of non-degenerate perturbation theory which we had studied in the first two lectures, and realize that what is easy about non-degenerate perturbation theory is the zeroth order equation not only tells you what your zeroth order energy is, which of course is nothing but the unperturbed energy eigenvalue, it also tells you what the zeroth order eigenket is. Now, what happens if, on the other hand, the eigenvalue epsilon n of H 0 is not non-degenerate but is degenerate? Let us say it is d4 degenerate. Then the eigenkets for that are phi n1, phi n2 up to phi nd, which we assume have already been orthonormalized. Now, what can you say about psi n 0? Well, all you can say about psi n 0 at this stage is that it is an eigenket of H 0 belonging to the eigenvalue epsilon n, which means it could be any one of these d, and not only that, it could be any linear combination of these d eigenkets. So, all that we can say at the stage is psi n 0 is some linear combination C1 with C1 C2 CD as coefficients of phi n1, phi n2 up to phi nd. So, at this stage the constant C1 C2 CD cannot be determined, because at least from H 0, the equation from the zeroth order equation H 0 psi n 0 equal to E n 0 psi n 0, you cannot say anything about C1 C2 C up to CD, because no matter what C1 C2 CD etc. are, this equation, the basic zeroth order equation, is still going to be satisfied. So, this is where the basic difference between degenerate and non-degenerate perturbation theory lies. In non-degenerate perturbation theory, the zeroth order perturbation equation immediately tells you not only the energy eigenvalue to zeroth order, it also tells you what the energy eigenket is. Here, that is yet to be identified. You need to find out what C1, C2 up to CD is in order to be able to say what the zeroth order eigenket is, and for all calculations to proceed, you do need the zeroth order eigenket. So, this is what we know about the zeroth order eigenket at this stage. It is some linear combination of phi n1, phi n2, phi nd, and so far we have no clue what C1, C2, CD are. Of course, if we insist on psi n 0 being normalized, we know only one thing about C1, C2 etc., that their mod squares have to add up to 1. Now, we turn to the first order perturbation equation in the hope that will somehow tell us more about psi n 0. Well, this is the first order equation from H plus lambda V acting on psi n, the left hand side of the Schrodinger equation. We got these two terms which contain lambda to the 1, H 0 which did not have any lambda, and psi n 1 which had 1 lambda. In addition to that, you have V which already came with its own lambda acting on psi n 0 which has no lambda. So, these two together give you the first order term. On the right hand side, E n 0 which we have identified as epsilon n comes without a lambda, that is acting on or multiplying ket psi n 1 which has 1 lambda with it. E n 1 lambda with it multiplies psi n 0, no lambdas, and of course these are the only two terms on the right hand side. If you go beyond the first order, of course there are more and more terms on the right hand side. On the left hand side you have only two terms, no matter how high you go in perturbation theory, at least in this version of the perturbation theory. Now, in non-degenerate perturbation theory, if you recall, we found out the eigenvalue E n 1 by hitting both sides by the bra phi n, which we knew was exactly the correct bra corresponding to the ket setting here. But now we have a problem. We do not know what this ket here is. All we know is that it's some linear combination of all these. So what we do is, instead of acting upon by one psi n 0 which we don't know, we are going to act upon this by all the d bras which correspond to this energy. So phi n1, phi n2, phi n3, all the corresponding bras are going to act on the left hand side of, on both sides of this equation. Of course, that will give us d separate equations to deal with. So what does any one of these equations, the ith one, look like? It simply is this equation acted upon by phi n I, the bra, on each of the terms. Now notice that phi n I, the ket, was an eigenket of H0 corresponding to eigenvalue of epsilon n. So when the operator H0 acts on the bra phi n1 from the right, you essentially get the same factor epsilon n out. Of course, you should really get the conjugate of epsilon n out, but epsilon n, as you all know, is real, being the eigenvalue of a Hermitian H0. So this term brings out an epsilon n. So you have phi n I acting on psi n1. On this side, of course, epsilon n just comes out and you have phi n I acting on psi n1. But these two terms on the left hand side are exactly the same, so they cancel out. This exactly was the stage where you could figure out what En1 was in non-degenerate perturbation theory. But here you are really not getting En1, you are getting En1 times the coefficient Ci, that is the coefficient of phi n I in psi n0, which we remember don't know yet. On the left hand side at the same time, phi n I v psi n0, well, I have just put in psi n0 as sum over j going from 1 to d, Cj phi n j, and this is what has come out. So instead of an equation which gives you En1, what this gives us is a bunch of d equations, and each of the d equations essentially look like this. On the left hand side you have Vij Cj summed over. I put in an n up here just to remind you that this is all in the subspace corresponding to epsilon n. So this is a d-dimensional subspace, and when you add up all these terms, which is of course this sum here, you get En1 times Ci, and Vijn is nothing but this matrix element. Now if you look at this a bit closely, or if you just write it out in full, what we have are d simultaneous linear equations, one for each value of I. So you essentially start with the first order perturbation equation, keep on hitting it in succession by phi n1, phi n2 up to phi nd, and this gives you d simultaneous equations. So v11 c1 plus v12 c2 and so on, c2 and etc. Now this of course cries out for a matrix description, and if you do that, you get something very familiar. You get a matrix made out of just these Vij components acting on a column vector made out of the C1, C2, CD is nothing but En1. Remember, the En1 is common to all of these, acting on C1, C2, CD, or multiplying C1, C2, CD. And this of course is nothing but a matrix eigenvalue equation. So what we are really doing here is this d by d matrix which I get when I take matrix elements of the operator V, the perturbation operator, between just the degenerate eigenstates corresponding to the energy epsilon n or eigenvalue epsilon n of H0. We get a d by d matrix, and this is nothing but the eigenvalue equation for this. So En1 is nothing but the eigenvalue of this, or nothing but one of the d eigenvalues of this d by d matrix, and C1, C2, CD would be the corresponding eigenvector. Now one important thing that helps us here is that this d by d matrix Vn, whose elements are this Vn ij's, is a Hermitian matrix. The proof is actually very simple. You just start with the jith element. Remember, for a Hermitian matrix, it has to be equal to its Hermitian adjoint, which means the jith element has to be the conjugate of the ijth element. So, what is the jith element? It is nothing but phi nj sitting on the left as a bra and phi ni sitting on the right as a ket of V. But this, of course, is a conjugate. If you swapped the bra and the ket, of course, at the same time you should have to replace V by V dagger, but V being Hermitian, that does not change. And then this is nothing but Vijn's conjugate, which completes the proof that Vn, this matrix, this d by d matrix, is Hermitian. And one great thing about Hermitian matrix is this: a d by d Hermitian matrix always has d real eigenvalues, and it always has d linearly independent, hence orthonormalizable eigenvectors. Well, not hence orthonormalizable, linearly independent orthonormalized eigenvectors. And these d eigenvalues of this V matrix are nothing but the first order energy correction. So, finding out the first order energy correction, which used to be just finding out the matrix element of V in the unperturbed eigenket for non-degenerate theory, becomes a bit more complicated in degenerate theory. You first have to form this d by d matrix by calculating the matrix elements and then find out its eigenvalues. Well, these eigenvalues may be distinct. If they are all distinct, then of course the d energies, which were energy eigenvalues which were all equal for H0, will no longer be equal after perturbation is applied. So, perturbation may lift degeneracy. Note the word may, because it might so happen that some of the eigenvalues of V, this d by d matrix, may still be equal to each other, and so then we will persist with some amount of degeneracy. And the corresponding eigenvectors for each of the d real eigenvalues are the coefficients C1, C2, CD that you will get. They give you the coefficients, well, I should not say are the coefficients, but they give you the coefficients of the dth of the d zeroth order unperturbed eigenkets for this problem. Of course, because you started with d unperturbed eigenkets, you are going to end up with d perturbed eigenkets, at least first order corrections, first order perturbed eigenkets. But remember, we are not even talking about the first order perturbed eigenkets. We are still talking about the zeroth order eigenkets. Just to recap this point for stress, in the non-degenerate theory, the zeroth order equation immediately gives you both the energy eigenvalues and helps you to identify what the eigenkets are. In degenerate perturbation theory, on the other hand, the zeroth order equation tells you what the eigenvalues can be, but if an eigenvalue is degenerate, it cannot uniquely identify its eigenket at that stage. Of course, you do not expect one eigenket, but you expect d eigenkets even after perturbation is applied. Well, first order perturbation theory helps you to identify not only what the first order energy corrections are, but actually even what the zeroth order wave eigenkets should have been. So, let us go on to figure out higher order results. Well, let us start simply with the first order eigenket. Remember, so far we have just figured out what the zeroth order eigenkets are. They are nothing but linear combinations of phi n1, phi n2, phi nd with C1, C2, CD chosen, so that the column vector C1, C2, CD is an eigenvector, one of the d eigenvectors of the d by d Hermitian matrix Vn that we wrote down a while ago. Now, let us return back to the first order perturbation equation. Strictly speaking, we are not going to higher orders right now. We are still stuck at first order, and we want to figure out now that we know exactly what Cheyenne zeros we have, because we have found out what the eigenvectors of Vn are, we start with one of them. So, there are d such eigenvectors, we start with the ith one. I of course here could be 1, 2, 3, any value. So this really is applicable to any one of them, but just to make sure that we are really looking at the ith unperturbed or 0th order eigenket, and what follows from that, I'm saying I'm putting an I in each of these terms, which of course this is the psi n0 I, the one which we are talking about. Psi n1 I is the first order correction to the ith unperturbed eigenket in this base. Remember here I just runs over all the D that we have found out. So of course En1 has no I to go with it, simply because all of them correspond to the En1 does have an I to go with it. So this should have been a comma I here as well. We are talking about the ith energy eigenvalue out of the D possible energy eigenvalues. So to find out the first order eigenket to the correction to the eigenket, we follow exactly what we did in non-degenerate perturbation theory. We apply an arbitrary bra phi m. Just to remind you, in order to find a ket, all you need to do is find out its projection or its component in the direction of the eigenkets phi m, eigenkets of H0 I mean, because remember H0 has a complete eigenspectrum. So if you know all the components of any ket in the direction of the phi m's, then you can just write down that ket in terms of the phi m's. That's a standard basis usage. But if I do that, what happens is pretty straightforward. You have seen this before, so I am just going over this quickly. Phi m acting on this will give me the energy eigenvalue, unperturbed energy eigenvalue epsilon m, and I have just brought this to the other side. And when phi m goes and hits this, of course this just gets cancelled. Remember, here we are assuming, I actually wrote down what we are assuming here, but I made a mistake by writing it down. I meant apply bra phi m which is not equal to the bra psi n0, any other bra, which means this is going to vanish. So this is the equation that we get. So please realize that there is a typo here, this should be not equal to. Now among these phi m's, the one thing that you have started by saying is that it is not the particular psi n0 I that you are looking at. So this is actually phi m not equal to psi n0 I, which is why this term has vanished. But among the phi m there could be two kinds of terms. It could be, phi m could be psi n0 j, but with j equals 1, 2 and in fact not d. D is not I is ruled out by what I said right now, but it could be any one of the other d eigenvectors that you have found out, other d minus 1 eigenvectors you have found out, corresponding to, when I say eigenvectors I mean the 0th order eigenvectors that we have found out, corresponding to the unperturbed energy eigenket epsilon n. So for them, or it could be any of the other eigengets of H0 belonging to a different energy eigenvalue. Now if phi m belongs to any of these degenerate eigenvalues, or at least 0th order degenerate eigenvalues, epsilon m and epsilon n would be equal, so this will vanish. But then we know that psi n0 j, which is what phi m is, v psi n0 I, must be 0 because we have diagonalized the matrix V, right? If we started with some basis phi n1, phi n2, phi nd, but we had found out some linear combinations which are eigenvectors of the matrix Vn, and if you use those eigenvectors as your basis vectors, then of course the matrix is already diagonal, which means this term will also vanish. So this is trivially satisfied if phi m belongs to the same energy eigenspace, is any one of the other d minus eigenvectors that you have found out. But what happens if phi m does not belong to that? So phi m is an H0 eigenket, but it is not one of the psi n0 j's. For the rest, epsilon m is not equal to epsilon n, and you can just simply move this to the other side, divide by epsilon m minus epsilon n and get this. So we get the projection of psi n I1 in the dash of phi m simply by this. This looks almost exactly like the non-degenerate result. The only difference is, in the non-degenerate case, we could find the projection for all states other than the nth. Here we find the projection, we can find the projection for all states except for the ones which are in the same degenerate eigenspace to begin with, which is of course a very good thing, because this denominator epsilon n minus epsilon m would have been a dangerous thing to divide by if we were in the same eigenspace. Then of course it would have been 0 and you couldn't have divided by it. So what do we know about psi 1 ni? Well, what we know is this: you take the phi m psi ni overlaps, which is just this term, multiply ket phi m by that, add up over all m, but you can only add up over those m's for which the energy, unperturbed energy epsilon m is different from epsilon n. In addition to that, you can have a whole bunch of whole piece which is a linear combination of the psi 0 n1, psi 0 n2, psi 0 nd, because those projections cannot be found out from the first order equation. This again is a direct reflection of what we already had in non-degenerate perturbation theory, except that there the unknown piece was just some multiple of psi 0 n. There was only one psi 0 n. Here this psi 0 n tilde just says it's some vector in the eigenspace of psi 0, eigenspace corresponding to epsilon n, which means it's some combination of psi 0 n1, psi 0 n2, psi 0 nd. So this is what the first order eigenket correction looks like. What about the second order energy correction? For that, of course, we have to write down the second order perturbation equation, which is the familiar one, the same one that we had used in the first lecture, and of course which we had applied in the second lecture. However, what you need to realize is that we have one extra index here, which is this I index. So of course each one of the d unperturbed eigenkets that we have determined now by using the C1, C2, Cd coefficients, which are the eigenvectors of the Vn, each one of them can potentially have different energy corrections. So En1 becomes En1 1, En1 2, En1 3 up to En1 d. Similarly, En2 1, En2 3, En2 d, and so on. And so similarly the eigenkets corrections are different, could be different at least for different of the i's. So this is the second order equation now, and in order to find out E2 ni, all I have to do is hit with the bra psi 0 ni, specifically this bra corresponding to this one. If I do that, this of course just gives me E2 ni. This term drops out because the bra acted upon by H0 just gives you epsilon n times the bra, which means the two epsilon n's cancel, and you are left with this. And now comes the crux. Remember, this formula uses psi 1 ni, and we have a piece of psi 1 ni, the piece which is in the original degenerate eigenspace, which cannot be determined by perturbation theory at all. So, but on the other hand, E2 ni is the second order energy correction, and this is what we want to find out here. But in order to see this further, what we do is use the fact that the phi m's form a complete eigenstate and just insert them, insert this complete this identity, this form of the identity right here between V and psi 1 ni. So the first term simply becomes sum over all m, this is the sum over all m, psi 0 ni V, then the phi m identity operator psi 1 ni. Of course, the second term here is simply minus E1 ni, which is just a number, times this particular projection. Now we can split up this complete set of states. This is sum over all m into two pieces. Those states which are not degenerate with epsilon n, and we are writing those with a prime here. So this sum only runs over those states which are not of the same energy, as at least unperturbed energy, as psi 0 or psi 0 ni, plus those d other states psi 0 n1, psi 0 n2, psi 0 n3, which we have here. So these psi 0 nj, psi 1 ni, these projections are very much there, and these are the things which perturbation theory has not been able to tell us, right? Remember, the projection of the first order energy correction in the direction of any one of the vectors in the degenerate space, that is something you cannot find out, because the first order equation simply became trivially 0 equal to 0 for that. But that is really not a problem, because notice that this is a diagonal matrix, which means the only terms that are non-zero here is where j is equal to I, and when j is equal to I, this term is nothing but E1 ni, the corresponding eigenvalue. So instead of sum, this becomes just one term where j is equal to I. So this is psi 0 n comma j, psi 0 n comma I, exactly the same as psi 0 n comma I, psi 1 n comma I, exactly the same as this one. Coefficient becomes E1 ni. So they just cancel, and because they just cancel, you are just left with this one term. And now this projection, psi 1 ni's projection in the direction of any eigenket of H0 except for those which have the same energy as the one level we are talking about, all those we had calculated. We could and we did calculate, and we just need to put in the values. Notice that these terms which we could not figure out from first order perturbation theory simply cancel out. So E2 ni gives a formula which you can definitely calculate. You get a formula which looks very similar to what we had in non-degenerate perturbation theory. There we had phi m v phi n mod square by epsilon n minus epsilon m summed over all m. Here this looks very similar, except that instead of phi n you have psi 0 n I, so the ith one, whichever one you are talking about among the d possibilities. And what is important is the sum here is a primed sum. It runs only over those states which have a different energy initially before the perturbation, which had a different energy from epsilon n. So the degenerate eigenspace is not being summed over, which is great, of course, because otherwise you would have had problem with the division by 0 here. So in non-degenerate perturbation theory, the sum is over all states which other than phi n. Here the sum is over all states other than the ones which are degenerate to the original one. So there is a great deal of similarity. All you have to remember is, not only do you drop the energy term, drop the term corresponding to the state that you are dealing with. In degenerate perturbation theory, you drop the term corresponding to all states which are degenerate with it.